All right. So welcome, guys. We'll talk about Bloom filters today. First, a few words about myself. My name is Ofek. I'm a team lead at Hexagate. Recently joined forces with Chainalysis. We're an on-chain security platform, so we'll talk about it during the talk we'll have now. And I'm from a background of FPGA engineering for all of the embedded engineers over here, and security researcher. So, just to convince you guys, for everyone here who didn't hear yet about Bloom filters, that this is not just some random, not very used mechanism. So it's super used in distributed databases. I'm sure everyone here heard at least once about Cassandra. Yeah, even in past versions of Google Chrome, which is entirely different use cases, it was used to block or optimize blocking malicious URLs. And on the Ethereum blockchain, it's used to optimize lookups inside blocks. So now that I got you guys convinced this is something worth listening to, let's jump into our topic for today. So first, I'll start off with the use case, or what got us at Hexagate to use actually Bloom filters. I'll explain and describe you the mechanism. We'll have a short deep dive into the internals of this mechanism. Finally, I'll show you an example, an actual example for you guys to go on into your projects and use Bloom filters. So, to start off with a use case, let me describe what Hexagate does. So, it's an on-chain real-time detection and prevention platform. Now, this is a pretty long sentence. Let's break it up a little bit. So, on-chain is on the blockchain. Now, what we need to know for this talk about the blockchain is that this is an open network on which users can interact with transactions. So users make transactions. These are batched up into blocks. Blocks are posted to the blockchain for the world to see. Pretty simple. Now, real-time. Now, why is real-time security so crucial in blockchain security? Because whenever an attacker finds a vulnerability and exploits it, the attacker can instantly get a lot of money and run away with the money. It can take minutes, even seconds. So real-time security is super important in the world of blockchain. And detection and response. So basically, we look at transaction, post it to the blockchain, and in real time make the decision, is this malicious? Does this employ a risk to one of our users? And then we can respond in real time and actually save funds. So if we put the blockchain and the transaction aside for a second, Hexagate is basically a real-time data pipeline, right? So basically, what we ingest is thousands of transactions per second, which I guess you all think this poses some serious scaling issues, right? That's a lot of data that we ingest. So what we do to handle these scaling challenges, we use the simple and very useful strategy of using filters, right? So basically, we want to create a funnel of the data, of the transactions, and as early on, I guess, get rid of the transactions that are not worth looking into. And as we go on and do more complex logic that involves high CPU and I/O operations, we want to do it and less data. Okay, so just to get a concrete example for something that we do, logic that we employ at Hexagate, let's take a super simple monitoring capability that we offer, fund transfer monitoring. So our users have blockchain wallet addresses. They configure these addresses in our system, and they want to get notified whenever these wallets make fund transfers that are unexpected and violates their rules. So let's say user wants to get notified whenever their wallet makes a transfer to an unknown wallet with a super high volume. That's a risk. They want to get notified in real time. So the logic here is pretty simple, right? We scan all of the transactions, and basically we check the rules the user defined on each and one of those transactions. So to get some perspective on the scales that we handled, so let's say all of our users combined have 100K wallet addresses, right? We store them in a relational database. That's pretty standard, nothing DBs can't handle. But from the blockchain side, there's very high scale. As I said, thousands of transactions, and some of these transactions are very complex, right? So each transaction could hold up, well, a transaction is basically some operations done in an atomic matter, so some transactions even have hundreds of fund transfers between different wallet addresses, right? So volumes are very high, And there are billions of active addresses on the blockchain, which I guess the assumption that we go by is that most of the transactions on the blockchain are not even associated with addresses that we want to monitor for this use case, right? This allows us to create the funnel that we talked about earlier, right? We can get a transaction, first look at the addresses that I guess take part in this transaction, and make the decision. Are these addresses monitored by Hexagate? If so, let's continue checking them. If not, we can get rid of them and move on as quickly as possible. So this is a pretty simple logic, and we want to do it, as I said, as early on, as quickly as possible. So we want to make the smart decision based on the addresses in the transaction, and based on if we monitor these addresses or not, if to skip or not to skip. So let's start with a naive approach for this problem, right? One naive approach would be, basically, whenever you get a transaction, get the addresses that are involved in it, check the database. If addresses are there, we keep looking in the transaction. If not, get rid of it. Now, this is not a very good solution. Why? A few reasons. One thing, it creates a high load on the DB, right? It means we have thousands of queries to the DB per second. That creates a heavy load for the DB. One other reason is it makes the pipeline, the data pipeline, pretty slow, because DB query is an I/O operation, is pretty slow. It stalls the whole pipeline. Now, I know you guys are thinking maybe we could batch up those operations, right? We could wait until 1,000 transactions arrive, then make a single query to the DB. That's not also good because still a very high load on the DB, and it increases the latency. So we have to wait until we get 1,000 transactions. It takes a little bit of time. It could increase the throughput, but decrease the latency. So not very good. Now, another approach, also I know you guys are thinking, maybe use a caching layer on top of the DB. This is also problematic because there's no cache locality. Now, what is cache locality? If we could assume that an address, whenever it makes a transfer, we expect it to make some more consequent transfer in the near future, what we could do is store the result in cache. Then whenever we see a transaction, we could check the cache, expect a cache hit, then move on. But we do not have this assumption. A lot of random addresses makes transactions in short periods of time. We could use a very large cache and increase the rate of cache hits, but it causes high memory footprint, which is also not good for us. So this is where Bloom filter comes to the rescue. So Bloom filter introduces kind of a different approach. It approximates this problem. It approximates the set membership problem. The set membership problem, of course, is if we have a set of items or the monitored addresses, in our case, the monitored addresses by Hexagate, we want to get another item, another address from the transaction and see if it belongs to the set, right? Pretty simple. And Bloom filter introduces a trade-off between the memory footprint and the false positive rate. Now, I know that sounds concerning, but we'll get right into what it means actually, the false positive. So, how does the false positive work? So Bloom filters, from a user perspective, works like this. If the item is indeed inside the set, then Bloom filter would always say, yes, it is part of the set. But if it's not part of the set, Bloom filter would mostly say it's not a part of the set, and sometimes it could say it is a part of the set. This is pretty simple, but from my perspective, this is how Bloom filter works. From my perspective as a developer, as a user, this is how Bloom filter works. No means no. This is what you guys need to remember from this, right? No means no, and yes means probably. So how do what does it mean for me? How do I use Bloom filter? So if Bloom filter tells me no, it means no. I can skip the transaction very fast, very simple. But if Bloom filter says yes, the address is monitored, then we have to make an extra check inside the database, an extra I/O operation to make sure we do monitor this address inside the transaction. So that's totally fine by me, right? Because what it basically means is that I make sometime, I guess rarely, I make an extra I/O operation, extra check with a database, but I get a very low memory footprint, which we'll explore in a second, how lower the memory footprint is. Okay, so now we'll have a quick deep dive into the internals of Bloom filter and how it actually works. It's a bit complex, so bear with me. So Bloom filter has two phases. There's the initialization phase. in which we, I guess, insert the items into the Bloom filter. And then there's the lookup phase. So Bloom filter is initialized. We can look up items in it and check out the set membership. So in the initialization phase, we basically start off with an empty array of bits, or I guess an array of bits, all set to 0. Then one by one, we take items from our set and insert it into the Bloom filter. So this is how the logic looks. So let's go step by step. First of all, we calculate k hash functions. So we have to calculate k different hash functions. I used I to make the hash functions a bit different. We use the result to get an index inside the array of bits. Then we set this bit to 1. So in the end, after inserting all of the items, we have the same array of bits, and some are set to 1. This is pretty standard. Now Bloom filter is initialized, and we can start looking up inside the Bloom filter. So how does the lookup work? So we basically do the same logic we did in the insertion, we do in the lookup. So we get an item, we have x, we calculate the same k hash functions, we get k pointers into this array, into B, and then we check, we visit all of these cells and check if all of them are 1. Now, if the item was indeed a member of the original set, then because we did the initialization in the same way, all of the bits must be set to 1. Bloom filter would always say yes, good. But if the item is not a member of the initial set, then some of the bits could be set to 0. Now, why could even some of the cells be set to 1? Because there could be a collision between one hash calculation on one item and another hash calculation on another item. There could be a collision in the indexes because we calculate. There could be a collision in the hash and in the modulo calculation. And then all of the bits could be set to 1, and we could get a false positive. So this is the internals of Bloom filter, but what we guys need to remember is that no means no and yes means probably. This is how we use Bloom filter, pretty simple. And one thing, I guess, if you guys listen closely about the implementation, then we cannot remove items from the Bloom filter, but this is totally fine, right? Because it basically means if we want to remove an item from the Bloom filter, we could expect a higher rate of false positives, but we do check the database. We could refresh the Bloom filter every now and then. Now, how to use Bloom filters? So I guess if you guys listened, we have a few constants we need to keep in mind. We have the probability for false positive. Of course, we want to keep it as low as possible. We have the number of bits in the array, which translates to our memory footprint. We have the items, the number of items in the original set. Now, why we do need to keep this in mind? Just to get a feeling, if, let's say, we have 100 bits, but we have, I guess, in the array we have 100 bits, but we have 1 billion items, then almost, I guess, we would expect all of the bits to be set to 1 and always get false positives. So we do need to keep the number of items in the original set in mind when using Bloom filters. Then we have the number of hash operations. We don't really need to worry about the number of hash operations because there's an optimal value for that. So I guess it's given for us by the other constants. So what we need to remember, the bottom line is, given a number of items in the original set, there's a trade-off between n, the memory, and p, the probability for false positives. Now, there's a formula for that. I don't expect you guys to remember it. You can look it up online. This is also just an approximation of the exact formula. But let's get back to the original problem just to get a sense of the numbers, of the memory footprint optimization that we got. So if you remember, m, the number of items in the set, is 100K, right? 100K addresses. P, the desired, I guess, false positive probability is 1 in 100. So I guess I could control P. I say, like, OK, every 100 transaction, I allow myself to check the DB. It wouldn't make my data pipeline too slow. If, I guess, trust me, the calculation is right. The n, the number of bits, is around 930,000 bits, which means 120 kilobyte. Now, just to get a sense of how much lower memory footprint that is, if we were to store 100K wallet addresses on memory, it would take us 2 megabytes, over 2 megabytes if we wanted to look up fast on this data structure. So this is over 20 times or memory footprint optimization. This is very useful. Now, how fast are these lookups? If we get up to the numbers that we saw before, then trust me, K, I guess the number of hash operation is 7, which is very low. If we look at Python, to calculate hash 7 times, we have very fast hash functions. It takes up to just a few microseconds. Memory access, also very fast. The Bloom filter lookup just takes just a few microseconds. And this is way faster than most DB lookups. Even if you use SQLite, it isn't fast as this. I guess we use Postgres, so much slower. And as we will talk about just in a bit, like a lot of great Python libraries, these are Rust implementations wrapped in Python. And I guess lookup speed when using Rust or fast languages could be super fast. ISO implementation was up to 50 nanoseconds of lookup time. This is really super fast. So now how to actually use Bloom filters. I guess you would like to go home and say, this is a great mechanism, I want to use it in my project. So there are a lot of Python implementations for Bloom filters. You can use Python Bloom filter. This is a pure Python implementation. As I said, we use the Rust implementation wrapped in Python, which is very easy to use inside Python projects. You can see in GitHub, there's rbloom and fastbloom-rs. Now, something very useful that we found is that Redis, even inside Redis, there's a natively implemented Bloom filter implementation. This is also good. It could be used across Dockers and pods. And let's see an actual example from the Redis Python client. So if we see, we initialize the Bloom filter, you can see that the bikes models is just the key of the set itself, or the Bloom filter itself. We could call it S or B. 0.01 is the probability for false positives that we initialize the Bloom filter with. This is M, the expected number of items to insert into the Bloom filter. And then we can simply add items into the Bloom filter. That would be A from the terminology before. And we can look up the Bloom filter, new items. So the key takeaways is I hope you guys saw this is extremely useful mechanism. You can use it in data pipelines, in DBs to optimize queries, many use cases, how to use, how to configure Bloom filter, and how to actually use in your Python projects. Thank you, guys.